Hi, welcome back. In this video, we are talking about confidence intervals, specifically confidence intervals of one sample proportions. So here we've got a question. An experiment finds that 26% of 53 subjects report improvement after using a new medicine. Create a 95% confidence interval for the actual cure rate. So we first want to talk about what is a confidence interval. So a confidence interval is, we're going to take our best guess of the truth, and we are going to add and subtract a margin of error. And that margin of error is based on a couple things. The first thing is, how good do I feel about this estimate? And that is based off of my sample size. So the larger my sample size is, the better I feel about this. So the smaller my margin of error could be. That comes in with this n in the denominator. The other factor that is going to come into play is how often I am okay being wrong. So what I mean by that is, if I really definitely need to contain the truth, being wrong is not an option, my estimate should just be from 0 to 100%. I don't want to miss anything. I need to be right. If I'm okay never being right, I'm just going to give you a single point value, which will almost certainly be wrong, because even if I say something like the true proportion is 65%, maybe the true proportion is 65.37128%, in which case 65% is wrong. So this value here, the Z star, is what is going to come in as my factor that captures how often I'm okay being wrong. So we're going to come back to that value shortly, but I want to get our problem set up. An experiment finds that 26% of 53 subjects report improvement after using a new medicine. So let's start out by defining my parameter of interest. I am looking at P. This is a true proportion. So this is the true proportion of patients who report improvement after using a new medication. I pulled this right from here. It's really important that we pull the context into this. And we see this is from an experiment, so there were some subjects in the experiment, but I'm really looking at the true proportion of all patients who are going to take this new medication. When I'm looking at what I have in my sample here, my sample size is 53, and I'm given a proportion. This is not the true proportion, like when we were looking at a sampling distribution. When we were doing sampling distributions, I knew the true proportion, and I was looking at how unusual something is. In this case, I don't know the true proportion. This is from a sample. I am interested in knowing the true proportion. I want to know if this is going to be an effective drug or not. So in this sample, P hat was equal to 0.26. So my Q hat is equal to 0.74. Now that P hat is equal to X over N, where X is the number of successes. So I'm just going to calculate X here. So how many patients out of the 53 experienced improvement? And so I'm going to rearrange this and take P hat times N, and I get 13.78. So I'm going to assume that that was 14 patients experienced success, and they just rounded that proportion. That's fine. So I'm also now told my confidence level is 95%. This is how I'm going to find my Z star value. That's this value. It's related to my confidence level. These are sometimes called critical values, and we are taking, basically, we're using a normal model, and we're saying, well, I'm going to take the confidence level, so this is going to be 95%, and I'm going to find these limits of it. 1 minus the confidence level we call alpha. So there will be alpha over 2 below and alpha over 2 above. If I want to find these values, they're going to end up being the same because this is a symmetrical model centered about 0, and they have the same area on the outside. So you will have a negative and a positive. So if I want to find this value on my calculator, I'm going to do an inverse norm, and I'm going to do the area in just one tail. My calculator doesn't have the updated operating system. So I am going to put in 1 minus my confidence level divided by 2, 0, and 1. And I'm going to put some absolute value signs around that because that's going to give me just the positive. There are 3 really common confidence levels, and so let's calculate what these are using this. So I'm going to do inverse norm, the area in just one tail. So the area in the middle is 95%, so both of these are 5%, so this is 2.5%. So 0.025, the area needs to be as a decimal. The mean is 0 and the standard deviation is 1. This is 1.96. For 99%, inverse norm, I'm going to do this as 1 minus 0.99 divided by 2. So 1 minus the confidence level divided by 2. Mean is 0, standard deviation is 1, and I get 2.58. And for 90%, 1 minus 0.9 divided by 2, mean is 0, standard deviation is 1, I get 1.645. These are the most common critical values, the most common Z-star values that you are going to see, but there can be others, so we want to keep this in mind. So for a confidence level of 95%, my critical Z-star value is 1.96. You do not need to show work to get this. You are allowed to just know it. It is assumed that you can make this connection here. Okay, so now that I have set things up here, I need to check my assumptions and conditions. These are the same assumptions and conditions that I was using for sampling distributions because I am going to be using a sampling distribution for my confidence interval. So for my check-ass, I first need to check independence. In this case, I have an unlimited population. While I've only had 53 subjects in this study so far, the population of people that I could give this medication to is unlimited. So I have an unlimited population, and it's reasonable to assume that my patients are independent. And not just that the patients, but the patient's responses are independent. So now I need to check my sample size. And when we're using for confidence intervals, I don't know the truth. I have no true estimate, or I have no true value of this. I just have an estimate. So for my sample size requirement, I'm going to check NP hat and NQ hat. So this is 53 times 0.26 and 53 times 0.74. Both of these are bigger than 10, so we are okay, and this is what is going to allow us to use the normal model. The next thing is random. And in this case, this is not a random sample. This is an experiment, and experiments are not generally a random sample. However, I am going to assume that there was random assignment to treatment because I am told it's an experiment. I'm going to assume this was a good experiment, not a bad experiment. So I'm going to assume that there was random assignment to treatment. So now that I have met my assumptions and conditions, p hat is approximately normal. So I'm done with my checking assumptions. So p hat is approximately normal. The mean of this distribution we know should be p based on our sampling distributions. However, I don't know p, I'm estimating it to be p hat. So I'm assuming the mean of this distribution is 0.26. The standard deviation of this distribution should be the square root of pq over n. I don't know p and q. I am estimating them with p hat and q hat. Because this is like a second level estimate, I'm using an estimate in a calculation to estimate something else. We're not going to call this the standard deviation anymore. We're going to call this the standard error. And you could think of this as the standard deviation estimate. So that's kind of what you can think of for standard error. So this value, if I plug in the numbers, is 0.603. My margin of error is this piece here, the z star times the square root of p hat q hat over n. So p hat, the square root of p hat q hat over n, that is just the standard error. So this is z star times the standard error of p hat. Well, z star is here, p hat, the standard error is here, so I can just calculate that to be 0.1182. This gives me a confidence interval, which will be the p hat plus or minus my margin of error of 0.142 to 0.378. On my calculator, if you go to stat test, you will see that there are tests and intervals. I am going to go down to one prop z int. I'm going to input x. This is my number of successes, and so we're saying that was about 14. This has to be a whole number. And then my n is 53. My confidence level is 95, and I will hit calculate. And it gives me 0.145 to 0.382. So these are very similar, and that likely has to do with some rounding that I did in the standard error and the z star value. But this is my estimate. So I'm not done here. Once I have a confidence interval, I need to interpret that confidence interval. So I'm going to verbally do the interpretation of the confidence level, and then I'll write down the interpretation of the confidence interval and then discuss the why is it so wide. If many samples of patients were taken and given this drug, so we're going to take many samples of patients, size 53, or so many samples of 53 patients. I'm going to give the drug and I'm going to record this cure rate. Then I'm going to create a 95% confidence interval estimate of the cure rate with all of those many samples. I would expect about 90% of the intervals I make from these many samples to include the true cure rate of the new medication. So the interpretation of the confidence interval, I am 95% confident that the true cure rate for the new medication for patients like those included in the study lies between 14.2% and 37.8%. This clause I put in here for patients like those included in the study. This is in there because I didn't have a random sample. Those patients who participated in the study are unique in some factors that caused them to participate in the study. So this might not be the case for patients who don't share those characteristics that got them to participate in the study. Now, this margin of error is really large. This margin of error is almost 12%. Likely, the interval is, and the margin of error is so large because my sample size is so small. So the 1.96, this is kind of fixed. I've stated how confident I need it to be. But the standard error is based on my sample size. And the margin of error is so large because n equals 53 is a small sample. So if I want to have if I want to have a more narrow margin, if I want to have a more narrow interval, I need a larger sample. In the next video, we're going to continue this example looking at margin of error.